Hello, we are a team from the University of Moratuwa, Sri Lanka, and we will be presenting on a screening tool for cardiovascular disease management in resource-constrained environments. And this is our team. Congenital heart disease or CHD is the most common type of birth defect. In Sri Lanka, more than 3,000 kids are born with CHDs each year, and more than 1,500 deaths occur due to lack of facilities. The most commonly available diagnostic tool for CHD identification is the stethoscope, which is used by doctors to listen to heart sounds. However, it requires experience and expertise to identify the CHDs only by listening to heart sounds. Additionally, the inability to clearly hear in noisy environments is also a challenge. On the other hand, we have the echocardiogram machine, which uses ultrasound imaging of the heart to view and identify a defect in the structure of the heart. However, it is time consuming and expensive. Therefore, there exists a need for a diagnostic tool that can overcome the challenges of these two methods. With that, we identify two types of biosignals that are useful in providing information about the heart. Phonocardiogram or PCG is the waveform of the heart sounds and it represents mechanical activity. Electrocardiogram or ECG, on the other hand, represents the electrical activity of the heart. And when combined together, simultaneous ECG and PCG can give us more detailed information about any defects of the heart and its valves, along with the exact location of the occurrence of that defect in the cardiac site. With that, we have identified our problem statement that there exists a need for an accurate, reliable, and noise filtering screening tool that can simultaneously acquire synchronized ECG and PCG signals, which also provide the ability to visualize them in a user-friendly interface.
This is our proposed hardware block diagram. This gives a summary of the components we selected for the implementation and also how each component is interconnected together. The transmitted Bluetooth data are then received by your mobile device. This data is then sent to cloud server for processing, which includes the signal denoising and disease classification steps. The preprocessed data is then sent back to the mobile app to display the denoised ECG and ECG waveforms and also the model outputs. Recording and playback functionality is also included in our design. Next, we will look at the demonstration of our setup.
This is our test setup for the prototype testing. Here you can see our custom made PCB for the STM32S7 microcontroller, and this is our PCB for our Bluetooth IC, which is RNBD451. To acquire ECG, we are using this ADS1298 evaluation board, and to power it, we are using this MMBO motherboard. To acquire ECG, we are using silver dry electrodes, and we have applied ECG gel. To acquire the heart sounds, we have made custom PCBs using MEMS microphones, and to further amplify the signal, we are using this Lichtmann stethoscope head. To transmit the signal, we are using this IC, and the simultaneous data will be transmitted to our computer GUI application.
This is our computer GUI. We use this for visualize the signal of our initial stage. Now we keep our device on the chest. Then we can show the simultaneous ECG and PCG signals on the GUI. This is the raw signal. Additionally, we provide the signal recording and denoising functionality. First, we check our recording functionality. Data is recording now. Now we stop the recording. Now we will check the denoising functionality. We will filter the recorded data. This is the filtered signals. In here you can see we removed the baseline wandering and also other noises. For that we use the band pass and band stop filters.
This is the 3D model of our prototype design. You can see the assembled and exploded view of the design. Now let's have a look at the assembly of the prototype. Now let's look at the mobile application.
This is the demonstration of our mobile application. First you need to log into the mobile application. If you don't have an account, you can register. You can enter the email and password to log into the mobile application. Then you click the connect device button. You can connect with our device using Bluetooth. This is our Bluetooth IC. You can select the option for display and we selected the simultaneous ECG and PCG. When we click the start exam button, you can display the simultaneous ECG and PCG. We test the signal with 10 seconds. After that it directed to the results screen. This is the patient detail screens. We did not implement it yet.
While our device supports captures ECG and PCG signals simultaneously, a machine learning based decision support system is particularly useful for non specialist users. As ECG and PCG signals can convey mutually exclusive diagnostic information, we believe that fusing both modalities could offer a more comprehensive assessment of cardiac health. So, we have implemented a model for detection of cardiac abnormalities using simultaneous ECG and PCG data. The model will use a window of these two modalities in a high-dimensional time-frequency representation known as scalegram. The model consists of two modality-specific encoders that will perform 2D convolutions and max pooling in the first stages to obtain feature vectors and combines the extracted features towards the latter part of the model and provides the classification of. We obtained a test accuracy of 82%, precision of 83%, recall of 93% with this model, which are comparable with the results in the literature. Additionally, we also propose a novel model architecture to make sure that both low-level and high-level synchronous features are utilized in the decision-making stage. In addition to the two modality-specific encoders, this architecture also consists of a fusion encoder which uses the intermediate layers of the two modality-specific encoders while progressing towards the classification. This is a more detailed diagram of the proposed classification model, and zooming in, you can see how intermediate layers are concatenated to build the fusion encoder. For model building, we are using the training A folder of the Physionet 2016 dataset, which consists of 406 recordings of simultaneous ECG and PCG data. So, in our project, we have completed up to the mic array design and denoising, and we are planning to do the system implementation along with the mobile application by April 2025. Thank you.